Okay, hello guys. I feel awful that you guys lost out on all the recordings from the last class, but so what I'm going to do is I found that I had a course review that I did at the end of the semester, and I'm going to do two recordings for you guys that cover that course review. I think it's more effective than reviewing all of the material in the course, and this really touches the highlights and I think it'll work out okay for you. So, main goal for the class, this is what I want you to get out of the class. So, storage is about abstracting old, small-scale, SCSI technologies. There's this old material out there, this old way to do things that still uh, provides a framework for how we do everything in storage. It's really based on that old technology. So we abstract all that to create huge storage environments to support the needs of modern organizations. Uh, that's definitely true. Storage is a combination of systems and networks, and hopefully you'll get exposed to that when you do the labs. And the goal is to understand the underlying technologies and the way that they're abstracted to create modern systems. So storage is all about um, uh, uh, the transition between the the uh, the physical layer of storage that exists on those spinning disks or SSD arrays and abstracting that to make it useful for really large scale, high speed storage uh, uh, retrieval systems. So the problem is, how do we go from that physical layer stuff to the logical storing that we do storage that we provide to the applications that exist out there. That's the main thing about storage. It's that how do you go from small scale physical data blocks to large scale, huge storage or huge amounts of storage that can be used by lots of different people. So got a bunch of assignments for the class, and the labs are a little bit different than what you see there, but not too much. So don't worry about the labs that if they're a little bit different than that. Storage challenges. Well, storage systems become independent systems requiring good management tools and techniques. Um, so the challenges that that you face include identifying and extracting meaningful information from multi-terabyte systems. So how do you go from these huge storage arrays to exactly the right file that you want? You want uh, a 5 kilobyte file, but you're trying to get it from a multi-terabyte system. How do you find that one little tiny file that may be one data block that in a storage array that's got millions of data blocks? How do you find that? Organizing disk and file structures for optimal performance and protecting large storage pools from disk crashes. If you only have those few data blocks that you want stored on one disk, what happens when that disk crashes? Because that's what disks do. They fail. And so how do you how do you build redundancy into the system to make it so that it can handle failures of individual and sometimes multiple disks at any given time and still provide service? So SCSI was the key idea behind all this stuff. SCSI is a let's see. So here's a SCSI parallel cable daisy chain. This is the basis for everything storage still. So the things to notice here is you've got that device 7 that says there, and it's got a CPU. uh, that's where an operating system resides. And that operating system thinks that it can connect directly to the data blocks that it needs to, answer a user request. But the problem is that that's not true, because between the CPU and the operating system and the data blocks are these extra pieces of hardware, like a SCSI host bus adapter. And that SCSI host adapter keeps track of what disks and what devices the data blocks are stored on that are the ones that you're interested in getting. So that SCSI host adapter is the first layer of abstraction between the operating system and the data blocks that it's looking for. And that concept of operating system thinks that it knows how to find something, but it really doesn't. That's what everything in storage is all about. It's all about that layers of abstraction built into the system to make it so that the operating system always thinks it knows right where the right file is located, but it never does. And we always have these layers of abstraction built in there to make it so that's useful. Now, in a SCSI environment, we've got that host bus adapter, which then has a 50 conductor cable. Yeah, these are the big wide cables, and that connects out to different devices that have SCSI disk controllers. And those SCSI disk controllers are set up in a daisy chain, which means that the request goes from one to the next, next, next. And if there's ever any break any place along the line, the whole thing is gone. Now, in this guy, we've got several devices, and we've got several SCSI disk controllers. Those are all layers of abstraction. So the SCSI host adapter thinks that it knows exactly which device and which location on which device it needs to go to get to the data blocks that it's looking for. But in fact, it doesn't. It all it knows is that it doesn't even know how many disk controllers are out there. It just knows that there's this bus, and I put the request out onto the bus, which is our 50 conductor cable, and it ends up at the right location. Then the SCSI disk controller, knows what data blocks are located on what devices that are attached to it, and then it knows how to find the right data blocks, and then forward those back to the SCSI host adapter, which then forwards them on to the operating system. Now, that terminator is only important from a SCSI perspective. The terminator had to be there in these old SCSI environments, or nothing would work. And it was basically a place where the signals would go and then get turned around and sent back to the rest of the cable. So a SCSI request started out like this. So you had a program generated IO request. So this was some sort of program, think of it as Microsoft Word, says, hey, I need this file, because the user clicked on File Open and saw a list of file names in there and clicked on one, and that generated a request, an IO request. That went out to the operating system. The operating system said, oh, okay, that's someplace out here, and dumped that request to the file system, sort of knows what's out there, but not really. And so it dumps it off to the SCSI driver. The SCSI driver dumps it to the host adapter, which goes to the SCSI bus, which goes to the SCSI disk controller, which goes finally to the SCSI disk, and then goes back up the chain with the right data that the user program requested. So, there's a lot of layers of abstraction in here, and there's a lot of parts of the system that think they know what's going on, but really don't. And because of that, this became the model for all the later storage systems. Because once you put a layer of abstraction in there, you can change everything. And you can make it so that you can expand the SCSI disk array to a huge number of disks. And that was the interesting thing about this, as any one disk has a finite amount of storage that it can supply. But if you can uh, connect this into a whole array, then you can have many, 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 many times that the amount of storage that exists on a single disk. So the next thing was to say, well, let's turn this into iSCSI. Now, in iSCSI, it looks the same. We've got our SCSI driver, our SCSI initiator subsystem, but then instead of connecting to our SCSI bus, what we do is we connect to TCP. And that means that we can connect to the internet, which means now we can have basically infinitely large storage systems available to us. So this layer of abstraction comes in again and says, you know, let's make it so the system thinks that it knows where it's going, but in fact it doesn't. By adding these layers of abstraction, the operating system doesn't know anything about the fact that we're crossing the internet to get the storage that we want from Chicago. Doesn't know anything about that. And as a matter of fact, when we add iSCSI to this thing, we don't update the operating system. There's no interaction with the operating system. We just say to the operating system, go ahead. And it's just now it looks like you've got this one huge disk out there, but it's a lot huger than it used to be. And that's the miracle of abstraction. Now, another little tiny technology that turns out to be hugely important in all this stuff is this idea of encapsulation. So when you have encapsulation, you have this request for SCSI data that goes out, but it doesn't know anything about the path that it needs to take to get to the actual data that it's requested. So that SCSI data request gets pushed out into a SCSI command, which hits iSCSI, which means internet. That means out onto a network, and then we keep that. The request stays encapsulated inside our Ethernet packet and our IP, our Ethernet frame, which encapsulates our IP packet, which encapsulates our TCP. I've forgotten what that's called, but it the request stays inside there so that these lower level parts of the request never know anything about the path that they're taking to be resolved. That's all handled by different parts of the network that that make this really useful. But at the end of this, we have disks, and each one of the disks that we have are partitioned, and each partition carries a bunch of areas in it. Now, there's an optional boot block so that if you have multiple disks on a single computer, only one of them is going to have a boot block because that's the part that contains the information to get the whole thing to actually work. Now, every partition is going to have a super block that defines the boundaries of the areas within that partition. So, what you've got on a disk is just a whole bunch of data blocks that don't mean anything. But you've got to have these things like the boot block that says, when the machine first contacts the disk, go to this data block and get the information that you need to boot from it. And, without that information, there's nothing. This is just a big bunch of ones and zeros. It doesn't mean anything. And the same goes for the super block, which says, it's a teeny tiny little area on the disk that says these are the boundaries of all the other areas on the disk. If you're looking for this information, start here. And then you've got a set of information blocks known as inodes. Now, this is in a Linux ext file system, and we use ext as the example just because it kind of gets you thinking about data blocks and addressing and all that kind of stuff. Uh, you'll see some limitations to it, but we still use it to talk about it because it makes a lot of sense. Then you're going to have a list of free physical blocks. It's called the free list. And then a whole bunch of data blocks that are free and used. And those are intermingled. Now, the thing that makes it so that you can find the free ones instead of the used data blocks is the list of free blocks. And that free list is accessed every time you wanted to find a data block that you can write data to. So just generally speaking, this is kind of a layout for what you see here, way out of scale, of course. And this one is because it's got that master boot record, this is a Windows partition. Uh, Windows works differently. The NTFS file system works differently than ext in that NTFS is organized like a big database. And as you remember from your database classes, any data, any record in a database, we use multiple tables to store records in databases so that we can have one data element in one table that connects out to lots of other data elements and lots of other tables. And what that means that we have these objects and attributes. Some objects have a very small number of attributes. Some other objects have a very large number of attributes. But because of the way that relational databases work, we can house that, kind of all together. And that's how NTFS works with its file system. It's an objects and attributes kind of thing, so that you can have lots of permissions associated with one file or just a very small number of permissions associated with one file. It's just a question of one object having many attributes or a very small number of attributes. But you can see that most of what we talked about on the previous page is still valid here. The boot blocks, the super block, the free space, the inodes. That's a weird drawing. It's got inodes and MBR. Doesn't matter. But so this is the basic idea for what happens on a disk. Now, this is kind of a different way to represent the inode table. And the inode table is kind of interesting in ext because it has a bunch of fields in it, but mostly you'll notice that it's a fixed number of fields, and the fields that exist in here are fixed in nature and are very limited. So if you look at the bottom of this drawing, we've got time last accessed, time last modified, and time created. And that's all that we know about these files. And so if you wanted to see who modified this file last, it's not there. We don't collect it. It's not there. There's no way to know that. And if you wanted to go back to see not the last modification, but the modification before the last modification, no way to know that. We never save it. There's no place to put it. That's it. So just like when we talk about uh, um, data packets and the fact that if there isn't a field in the header of a data packet for something, it isn't stored. Same thing applies here. So if you don't see it in these fields, it doesn't exist. Now, the things to notice here are things like the file size. We've got 32 bits to deal with, and this is ext 3 or 4. I think it's the current version is like 6. So everything that you'll see here in later ext versions is just bigger, but it's essentially the same sort of model. So some of the things that you'll notice is that up on top, we've got a link count. Well, that link count is half of 32 bits, so that's 16 bits. How many links can we have to this? Only 16 bits worth. How many links can we get with 16 bits? Well, 2 to the 16th, which is 65,000. Well, that same logic applies to the user ID and group ID. We only have 16 bits to work with, and so that means we can only have 65,000 user IDs in this ext file system. Is that enough? No, it's not, as a matter of fact. So that's why companies don't use this particular version of ext. They use bigger versions of ext. And the same thing goes with file size in bytes. So we've got 32 bits we've got to work with. Well, if your file size is limited to the number of bytes you can fit into 32 bits, what you're limited to is about 4 gigabytes. That's your maximum file size. Is that big enough? No, of course not. So, this doesn't satisfy the needs of modern organizations, but it does point to the idea that, if you can't fit it into this table, it can't be done. That's the important part of this drawing. Now, the other thing about this drawing is that one thing you'll notice that's not here is the file name. Where's the file name? Well, that's stored in a secondary directory file, and that directory file we'll get to in a second is kind of interesting because all that it stores is file name and the inode table number. So this inode table is replicated for each one of the files we have out there, and so to find the right inode table number, you have to look in the directory file, find the name that you're looking for, and then look at the inode table number, and then go to that particular inode table number. So this is the way that you deal. Other thing to notice here is that we've got room for 10 data block addresses in the inode table. Well, that's not enough. So how do we address bigger files? And the way we do it is like this. So we have the 10 disk addresses that stay right in the inode table, and then we'll have an indirect block so that one disk address points to another location that has another listing of 10 or 15, I can't remember, inode table entries that, or I'm sorry, data blocks, and so one address in the inode table points to another data structure that has 15 more data block addresses, and then a double indirect, one entry in the inode table points to another data structure that then points to another series of data structures, and a triple indirect, you can see where that goes. And so this is how we store the addresses, the data block addresses for large files using this small inode table data structure. So the mechanics of working our way through this, how do we use the inode table structure and the data and the directory file structure? This is how it works. So here's our root directory. What we're looking for is we're looking for /usr/ast/mbox. How do we get to that correct inode table number? Well, start in the root directory. In the root directory, we look for the /usr subdirectory. We scan down the root directory file, and we find USR is in inode table entry number 6. We then go to inode table entry number 6, and we see the mode, sizes, and times, just like at the top of the field there. And then it says that /USR is in data block 132. Then we go to data block 132, and we find that we're looking for /AST, and we scan down the data block 132, and we find that /AST is in inode table entry number 26. Then we go to inode table entry number 26, and we find that /UST is in data block UST/AST is in data block 406. We then go to data block 406, and we're looking for the mbox file. So we scan down the right-hand side, we find mbox, and we see that that's in inode table entry number 60. And then we go to inode table entry number 60, and that will give us the addresses of the data blocks that represent the file /USR/AST/mbox. A little confusing, but you can see that this very simple data structure gets us to one inode table entry and one set of data blocks within just a few short hops. And this could be on some huge storage array, but it gets us there in 3 hops. That's pretty good, even though it's a little confusing to us. But this is something computers can do pretty well. So file sizes and access methods. So if in the default block size for this ext4 file system was 512 bytes. Well, what does that get us? 512 bytes. By the way, the default block size in NTFS is 4012 bytes. What would that mean? What does that have to do with anything? Well, that means that if we've got a teeny tiny file in our ext4 file system, we can store that teeny tiny file by using just 512 bytes on our storage device. But that same teeny tiny file in an NTFS file system, we would have to allocate 4012 bytes just to store a single teeny tiny file, like a touch 0-byte file. Now, 4012 bytes just for a 0-byte file? Yeah, that's wasteful, right? But that's the way that it works. Now here, I don't know if it's good or bad, but here we've got a block size of 512 bytes, which means that our teeny tiny touch file still uses 512 bytes. And there's nothing we can do about that because that's our smallest file size. Now, the other thing about this is that all 512 bytes needs to be read anytime you want to access this 0-byte file. And in NTFS, you've got to read 4012 bytes just to access this 0-byte file. That's crazy, but that's the way it goes. And you can see our indexing works and that kind of stuff. So our directory structure is a binary file that contains just the file name and the inode number. Directory entry consists of a block of 32-bit words, and blah blah blah. And so there's our directory file. So the 2 data structures that you have to deal with are inode table entries and directory files. Now, what happens? So that's the end of one lecture and into another one. What would happen if we were to put some intelligence out in our disk subsystem someplace? What are some of the problems that we run into when we have direct attached storage? Well, when you have if you rely on only the storage that can be attached directly to your server, the problems that you have are things like limited disk space. We can only put so many disks into a single box. Limited read, write, seek speed. If we have a limited number of disks and they all have that little arm that zips back and forth across the surface of the platters, then it can only go so fast. Our platters can only spin so fast. And if you need to find a file in a fragmented disk structure, then you've got that little wand going back and forth and back and forth and back and forth, trying to find all the data blocks. That's really slow. We have very low tolerance for error. When uh, uh, if we only have a limited number of disks that we can attach to a single server, then anytime we lose one of those disks, and we always lose disks, and we always plan for disks to fail, then we can only build so much redundancy into that system. And then we also have a single point of failure because that whole box is a single point of failure. And so if we had intelligent disk subsystems, hopefully we could get around some of the problems that we have of direct attached storage. So what would happen if we placed some intelligence in a disk controller and presented an abstracted version of the physical disks of the operating system? Well, why would we want to do it? Those problems we have with the limited storage space that we have in when we have only direct attached storage. So how could these problems be addressed through an abstraction layer? How is this similar to a virtualized environment? Where does the intelligence to implement this have to be placed? What's the relationship between the disk controller and the operating system? Besides an intelligent disk controller, what other capabilities might be nice to have? This is the justification for large-scale abstracted storage system. These issues right here, the problems associated with direct attached storage, is what makes you want to think beyond that. And intelligent disk subsystems allow us to get beyond those problems, and of course generate other problems, but get us to the point where we can deal with these issues here. And then these are some of the questions that you need to ask. Where do you put this intelligence? What's the relationship between the disk controller that's already there and the operating systems? How does all this work together? So if you use an intelligent storage system properly, you get all of these extra things. Increased capacity. Why? Because you're not limited to what fits in the box. Improve performance because instead of sending a write request to only one or a small set of disks, we can break that read or write request up to send it to lots of disks all at the same time. And therefore, we're not waiting for one disk to do its thing. We take this huge write request or read request and we send it out to a whole bunch of disks. And that means that each one of those disks is only doing a small portion of the read or write request. That means we've got much better performance. We got easier data management because we're not managing a single disk or a small number of disks. We're managing a whole bunch more robust backup and restore capabilities. And then finally, what companies are really interested in is improved flexibility and scalability. So the question comes down to this: what does the host see? So if you think of the hosts over here on the side here as looking through a little pipe, all right, and that's their wire that connects them to them. What actually exists in our intelligent storage system is this cache, back end, and a whole bunch of physical disks, and it's a complex environment. But what does the host actually see? The host sees none of that. All the host sees are the LUNs, the logical units, that are assigned to it. So even that top host doesn't see LUN number 2. As far as that top host is concerned, LUN 2 doesn't exist. The only LUNs that exist are 0 and 1. And for the bottom host, the only LUN that exists is LUN 2. LUN 0 and LUN 1, they don't even exist, let alone can be accessed. Now, where do these LUNs exist? Well, they're hidden. They're way back inside our intelligent storage system, located on physical disks. Now, in this drawing, we've got LUN 0, 1, and 2 on the same physical disk, but they could be spread across multiple physical disks also. Now, the reason we have a cache in front of them and a back end that takes requests and then forwards those requests to the correct physical disks is that that cache gives us a lot of capabilities. So if that top host sends a write request to LUN 0, the cache can receive that write request and forward it back into the back end and then to the physical disk. But instead of waiting to hear back from the physical disks that in fact the write request was successfully executed, the cache can receive the write request and then just reply immediately, done, written. Has it really been done and written? No, but the cache is going to take care of interacting with the back end and the physical disks. But by the cache responding and saying, yes, done, written, what that does is that frees up the operating system to move on to its next task. Because when it issues a write request, it blocks. It says, I'm issuing a write request. Now I'm going to wait to hear back from the disks that the write request was executed successfully. And by having a cache in there, it doesn't have to wait. The cache says, this is my job. I'll take it over from here. So there's a nice SNIA, the Storage Network Industry Alliance, is a I was going to say partisan, but it's a generic industry organization for storage. And they come up with this storage model that says that we're used to all these storage arrays and stuff. They think of the EMCs and Toshibas and the IBMs and stuff, telling us all this complicated stuff that their system does and nobody else's system does. But in fact, there's a generic set of things that has to happen, and yeah, different storage systems may do it differently. Forgot EMC. But in fact, the same things have to happen, and there's not much difference. So in this case, we've got this storage network industry alliance storage model, and it's a generic model that talks about what needs to be done. Now here we've got our application layer, we've got our file/record layer, and we've got our storage devices, and then we have blocks on the bottom. Our storage domain takes everything from the application layer down. That's our storage domain. Now our file/record layer is interesting because we're used to file systems, right? FS, where it says over there. But this one has database, DBMS. And why would you do that? And it turns out that database management systems do a lot of things that are very similar to file systems. But in a large scale database, like, think Oracle or MySQL or something like that, there is no file system behind it. The database management system takes care of interacting with the file systems and with the storage architectures, and so there is no file system there. Now, the reason this thing has that funny overlap is, think about something like a Microsoft Access database. Microsoft Access databases run on top of NTFS. So they're kind of like a database management system, but not really. And that gets at the problem that you have with an access database is that it's just not multi-user. So anyhow, so now we've got our application on top, and the application on top has a bunch of different ways to get to the storage devices on the bottom. And this storage model is all about the different ways to organize this process, because this is all about organization. We could have a database management system where the application interacts directly with the storage system through the database management system. Then same with the file system. And think of that as a small scale environment. But we're not really interested in that. Oh, and here we've got services that cover the whole storage domain. Oops. Yeah, but think about other kinds of architectures where we have an application that interacts with a file system that then interacts with a host environment where we've got a network, and we've got devices, and that host does things like block aggregation, where it takes the data blocks available on a whole bunch of storage devices and aggregates them to present them to the application as one large pool of storage environments, not a whole bunch of small individual devices. Okay, so all right, let me go on from there. And here we've got NAS, Network Attached Storage. Now, the difference between NAS and SAN is that you'll notice that our NAS appliance is like any other device on our local area network. That's the, that's the big distinction, is the NAS devices on the local area network with everything else. Now, a fiber channel SAN, just call it SAN, storage area network, is different in that in a SAN environment, you've got a local area network, and on that local area network are our PCs and our workstations, as well as our application servers, okay? They're all on that local area network. But behind those application servers, that's the SAN. The SAN is a way to connect storage arrays, storage devices uh, amongst themselves in such a way that the application servers aren't involved in those connections. So if our RAID 5 array on our iSCSI switch needed to connect to our robotic tape library, it would never touch the local area network on its way from the RAID 5 storage array to the robotic tape library. So the storage area network is that. It's a network, but it's only for the interconnection of storage devices. The reason that's so good is because a lot of the times when storage devices need to connect amongst themselves, they're exchanging really big files. And when you exchange really big files, you tie up the network. And that's only a problem if you have user traffic that's also trying to use the network at the same time. So having a storage area network is a great way to free up your local area network for just users interacting with application servers, which is our normal way to do things.